Good morning, one and all. I am Nisha Rathi, Assistant Professor, Department of Computer Science and Information Technology, Acropolis Institute of Technology and Research, Indore, is here before you to discuss my knowledge about a very important topic of data structure, that is AVL trees. The agenda of this lecture is to discuss on why there is a need of AVL tree if an equivalent efficient binary search tree is available. What exactly is AVL tree and what are the different characteristics of it? Balance factors, those are considered to be the backbone of AVL tree in balancing, and the rotations involved in the balancing of imbalanced trees. At the completion of this lecture, you guys will be confident to find whether there is certain critical imbalancing in the binary search tree or not. And if it is there, then what sort of imbalancing it is. Also, you will be able to apply the appropriate AVL rotation and can find out what sort of contribution these rotations are there for limiting the height of overall tree. For studying this subject, you have to have the knowledge about binary search tree, the methodology used to create a binary search tree, and the idea about the minimum and maximum height of it. We've already gone through the concept of binary search tree, where it says the maximum height of a binary search tree will be n minus 1, that is nothing but a skew, and it is a resultant of having some sorted or unsorted, sorted input in reverse order or sorted input. And the minimum height will be the resultant of some balanced binary tree. Fine. So this will comprise the best case as well as the worst case of your binary trees. Here we are discussing about the best case. The best case of our binary tree says it is highly balanced. Does mean your input's middle element is exactly the root element. Everything at the left hand side are the elements lesser than this root element, and everything at the right hand side will be the elements bigger than this root elements. If this is the case, if such type of input is there, then there is a possibility of having order of log n complexity for this BST. But this is not the case with your worst case. It says if your input is sorted or reverse sorted in order, then the resultant will be skew. It is nothing but just like your linear search, where there is a possibility of order of n complexity for searching certain elements. So this will be the worst case. So as a user, we are not able to find whether the input will be randomized or sorted or reverse sorted. So there must be some mechanism so that the resultant should lead to this balanced, almost balanced tree. And here is one of the solutions, that is AVL tree. Fine. Its name is given on the name of inventors, that is Edelson, Welsky and Landis. It is AVL based on the name of inventors. This AVL tree is a height balanced tree. It says the height of its left subtree and the right subtree will differ by at most 1 only. Fine, there is no possibility of any skew or difference in height more than 1. The self-balancing binary tree, it is termed as self-balancing because based on the values of the balance factor, the permissible values are 0, 1 and minus 1 only. If other value than these permissible values are there, then automatically it will apply the appropriate rotations for balancing the tree. That's what is termed as self-balanced binary search tree. Now here we are looking for what exactly is the balance factor. It is nothing but the difference in the height of left subtree as well as right subtree if we are looking for the balance factor at particular node. So 1 does mean the height of left is more than height of right by 1. 0 does mean both the subtrees are at the same height. Minus 1 does mean the height of right subtree is 1 more than the height of left subtree. So only 3 permissible values are there, 1, 0 and minus 1. Here we are looking for an example. See, for the leaf node we are all aware that the leaf node has no left or right subtree. So since the height of left and right subtrees are 0, so we can directly put the balance factors of all the leaf nodes as 0. How about the internal nodes? See the node 50. We can have the assessment what exactly is the height of left subtree, since it has to reach to this leaf node by traveling a single edge. So the height will be 1. How about this right subtree? From 50 you need to reach to 75 and then to either 65 or 75. So 2 edges need to be covered for reaching from this particular node 50 to any deep leaf node. So the height will be 2 and the difference of these two will be -1. So directly we can say this right tree is having one more height than this left subtree. Similarly for this 75, since the height of left subtree is 0, the height of right subtree is 0, so the resultant will be 0. The difference of the two will be 0. How about this 150? 150 having left height as 1, right height as 1, so the resultant will be 0. Here mistakenly I have said that 75's left tree subtree is having a height of 0. No, it is balance factor 0, but the height is 1. Here also the height is 1. Fine, so and the resultant is 0. How about this 100? We'll go for the deep leaf node only. So here for the deep leaf node, here 1, then 2 and then 3. So the overall height of your this right subtree for this node 100 will be 3. How about this right side? The right subtree is having a height of 2. This is 1, this is 2. So the difference will be 1. Here we can assess that, we can observe that the overall nodes are having the height balanced factor value as the permissible values, that is 1, 0 or -1. So the overall tree in the given example is balanced in nature. Fine. Now let us take one more example where we have three numbers 10, 20 and 30 with us. If we are making the different sequences with these three combinations, then the one of the sequence will be 30, 10 and 20. It says whatever be the very first element will become the root. This is the concept of your binary search tree. The next element, if it is lesser than, will take the part of left subtree. So here it will be the part of left subtree. Again, if you want to have the insertion of this 20, then compare this 20 with 30. Since it is lesser, go to the left side of it. Since 20 is greater than this 10, so it will take the right side of it, right side part of it. Fine. So the overall tree will be this. Apply the balance factor over here. Here the leaf node is 0. This 10 is heavily loaded with at the right subtree, so the resultant will be -1. The difference of left and right is 1 only, so this will be -1. Here for this 30, there is no right subtree, so the resultant will be the height of left minus height of right. So here it is 2 minus 0, this is 2, so it is imbalanced in nature. Similarly is the case with this 10, 30, 20 sequence, this 30, 20, 10 sequence, and for 10, 20 and 30 sequence. Let us go for the other sequences like 20, 10, 30 and 20, 30 and 10. Here we can say the resultant tree will be balanced since the middle element of the given tree number is taking the root position, so it will be balanced in nature. Now our task is to have, AVL says our task is to convert this imbalanced tree to the balanced one. See, what could be the way? Here we can see 20, if 20 is getting, the middle element is getting the middle position or the root position, then or the parent position, then there is a possibility of having the balanced tree. So here are the possible combinations. We have to have this 20 at this root position. So how to do this? First you have to take 20 to this position, then from this position to this position. You can see this whole conversion of this particular tree to this one will lead to rotation of this 20 to this direction in the right direction and then to the left direction. So this will be the type of rotation that will lead to the balanced tree like this. Similarly for this tree, again there is a requirement of two rotations. One from left rotation, the other will be right rotation, or either for the next two trees there is a requirement of a single rotation since 20 is at the internal node. Fine. So if we can have this in this 20 at the root position with one rotation on. So the concept we have discussed here is nothing but the rotations required for balancing the imbalanced binary search tree. Fine. To make it something like this, and it ensures that the result will be able to released in log n time only. Fine. So let us discuss more about the rotations, type of rotations. Here you can observe that there are certain concepts where there is a requirement of single rotation, and other way there could be more than one rotation. It comprises of two rotations. So the basic rotations are divided into two categories. One is single rotation, the other is double rotation. Single rotation says there are two possibilities, left to left rotation and RR rotation. Let us see what exactly it is with an example. See, this is one of the example. This is an example tree which is a binary search tree. Here if we want to have insertion of 5, then 5 will be compared with this 20, then with 10, then with 7. Since it is lesser than all the 3, so it will be inserted at left side of this 7. Fine. Now apply the balance factor. While applying the balance factor, we can observe that the balance factor of this 2 is, this 10 is 2, which is not permissible value of your balance factor. Fine. This makes this tree as imbalanced. Now what is required to make it balanced? First of all, this particular element is responsible for making this balanced tree as imbalanced. So we have to move this element. We have to shift this particular element in certain way so that the resultant should be balanced. Now, with reference to this imbalanced node, we have to assess to which direction this new number has been inserted. This new number 5 is nothing but the left child of left subtree of this 10. I am again repeating, this 5 is nothing but a left child of left subtree of this 10. So the type of rotation, since it is the left child of left subtree, the rotation is termed as LL rotation, and a single rotation is required that you have to perform here. This 7 is to be rotated in the direction left side and should be shifted to the position of 10. As 7 is moving upward to 10, so 10 will be automatically goes down and will take this position. So the resultant tree will be balanced tree, and it is nothing but a LL rotation. It is just because of the assessment that the newly entered element is nothing but a left part of left subtree of the imbalanced node, the deep imbalanced node. Let us see another example. Here is a tree. If we want to add 43 to it. Now 43, since 43 is bigger than every element at the right hand side, so 20, 30 and 37. So 43 will get the become the part of this right subtree of this 37. Now on applying the balance factors, we will get that from deep to upside, we will get this 30 as the first imbalanced node. Fine. So this is the reason, because of the insertion of this 43, this 30 node will get imbalanced. Fine. This is the deep node, the very first node that is imbalanced. Fine. So what we need to do, we need to find what was the reason for this imbalancing. The reason is this 43, insertion of this 43, which is right child of right subtree of this 30. Since it is a right child of right subtree, so the rotation will be termed as RR, and it is a single rotation. You have to move this 37 in place of 30, and this 30 will move down. So the resultant will be like this, and this is the resultant balance tree. Fine. Now there are possibilities of double rotations. Fine. So the double rotation says, it will be double. Double rotation says if there is insertion of new element which is causing the imbalancing is at right side of left subtree of the deep imbalanced node, then we have to apply two rotations in sequence. Fine. Again I am repeating. The insertion of this 9 leads to the imbalanced tree, and it is because this 9 is right child of left subtree of this 10. So here the rotation will be termed as RL. Why it is termed as RL? Let us see. Out of these two, we have to apply the rotation on the leaf node. Fine. That is responsible for the imbalancing. So this first rotation, since you are moving the right child, so this rotation is termed as R rotation, and because of this rotation, the 9 will get place of the 7 and 7 will move down. This is the application of this first rotation, that is R. For the second rotation, you have to move the left child of this particular 10. So this will be termed as L rotation. So here the direction is this. 9 will take the place of 10 and 10 will goes down. Fine. So the overall tree will be balanced one. See, for having this implementation, you have to have the consideration of two rotations in sequence. Similarly, you can go for LR rotation. It says the imbalance is there because of the insertion of some element which is a left child of some right subtree of the deep imbalanced node. Deep does mean there is imbalancing here also, but we will move from the node which created the imbalancing to the first node, up in the upper direction to the first node which is imbalanced. That's what is termed as deep imbalanced node. So with reference to this, you have to have the assessment to which direction this particular node has created the imbalancing. Fine. After insertion. Fine. So what you need to assess, since it is a left child of right subtree of this deep imbalanced node, therefore you have to have the implementation of two rotations. Now the very first rotation will be of the element that is being inserted. So here the 12 will be moved up in L direction. This is the L child that is being rotated. That's why it is termed as L rotation. So 12 will get the place of 15. 15 will goes down. Again you have to apply the second rotation. 12 will move up and 10 will move down. So the resultant will be the balanced tree. So these are the four types of rotations we have studied. One is LL rotation, the other is RL rotation, LL and RR rotation. All the two types of rotations are single rotations, and the other one are RL and LR. These are the double rotations, and the resultant are always balanced tree. And these balanced tree ensures us that the overall computed time will be log n only. There is no possibility of any skew. That's it for this lecture. In next lecture, we will cover the insertion, deletion, traverse and search operations on your AVL. Thank you.